Thank you for the very precise introduction. So I'm very glad to have this chance to introduce our 1 micron fiber ytterbium femtosecond fiber laser, which has a beautiful name, SONATA. So my first slide will be why we need SONATA. So SONATA is a 1 micron laser which has a relatively low power, but is very reliable and stable. So in principle, this laser can be a seed laser for a very high power ytterbium amplifier laser system, like the MOPA system, which laser can be the seeder for the huge amplifier chance afterwards. And what's more is like if you care about synchronization for the large laser facility, for example, like free electron laser facility and the extremely live infrastructure, you need to synchronize laser to laser together and to laser to the facility RF reference together. Then you need a no noise laser which has the function to be synchronized. So we provide a solution which has a very low noise laser and has a good performance for synchronization. And you can also use for any lab experiment, for example, pump pro experiment or other time critical experiment. So this laser has a simple structure, as you can see, it including a oscillator plus a preamplifier, and the laser have two output. The first output is the free space output. It has more than 100 milliwatt, and the output pulses is below 150 femtosecond transfer limit. And another output, we call it the fiber output, basic is from here, and the power is more than 10 milliwatt, and the pulse is chirp, and it's more than 3 picosecond. So this laser will be an ideal laser for amplifier from the fiber output, while you can use the free space output for synchronization to the facility or to other laser. And here I want to emphasize advantage of this laser. So this is a single compact unit with electronics and optics all integrate into the same housing. So you just need to plug in the cable and turn it on, and the laser will be start in 30 seconds. And we don't need to do any alignment. It's hands-off operation. And meanwhile, it has very low timing jitter of pulses and very good intensity and performance. So we do here where you can see the output spectrum from the laser, which has a perfect Gaussian shape with more than 40 nanometer spectral bandwidth and center at 1030. And the output spectrum pulses has below 150 femtosecond and is a transfer limit shape. And the laser is centered at 40 megahertz. So if people want more repetition rate, we can customize for them. Here we do some measurement for the free running repetition rate drift. Use the frequency counter to see how good the repetition rate is, how stable the repetition rate it is. So we do a logging for 10 minutes, and it find out the standard deviation of the repetition rate only drift 0.3 hertz. So which means it's 0.03 ppm at the stable room temperature. So when I say stable room temperature, actually our lab is plus minus 1 degree. So within plus minus 1 degree, the repetition rate drift below 1 hertz in 10 minutes. But if we do longer logging for the repetition rate, it's drifting from 0 to 5 and drift back to 0. This is most likely due to the fluctuation of lab temperature, but it's within the range of 10 Hertz, which is 0.25 ppm at the room temperature. And for this very small drifting, the laser actually is very easy to be synchronized and locked to any other lasers. And here we also measure the power log of the laser output, and we find out the power fluctuation is below 0.05% for logging of 150 hours. And for the short-term intensity noise, we are measure the laser intensity noise with the signal source analyzer with the fast photo detector. And as you can see, the integrated intensity noise from 10 Hz to 20 megahertz is 0.025%. So this is a very low noise as far as I can understand. And with this performance, we try to do some measurement with the laser's timing jitter because this is what we care about for a synchronizable laser. And try to when we want to measure the timing jitter, we have to use this setup from cycle. So we have to lock two lasers together with our BOC, which stands for Balanced Optical Cross Correlator, which is a very sensitive timing jitter error detector. And with this timing jitter error between the two lasers, we're sending the error to our electronics, feedback electronics, and the electronic feedback to one laser by locking them together to three with a feedback bandwidth of 3 kilohertz, which means below 3 kilohertz, the two lasers are very synchronized, so we can calibrate the residual timing jitter between the two lasers from 3 kilohertz to 20 megahertz, and the measurement turned out to be 2.5 femtosecond between two lasers, the residual timing jitter between two lasers. If you consider the symmetric of two lasers is exactly the same, so the individual laser's timing jitter is half of this number, which is 1.3 femtosecond. But this number is still a little bit higher than the reality because the detector noise floor is also contribute to 0.7 femtosecond. So I will say each laser probably have 1 femtosecond jitter integrate from 3 kilohertz to 20 megahertz. To prove the ability of SONATA to lock to other wavelength lasers, we also test the locking between SONATA and Zupano. And Zupano is another laser in our company, which at 1.5 micron with 80 megahertz repetition rate. And we use this TC-BOC, which is a two-color BOC to lock two different wavelength lasers together. The schematic is the same. And this is the sensitivity curve of the TC-BOC. By locking using 3 kilohertz locking bandwidth, we can lock these two lasers to below 6 femtosecond. And as you can see, this noise spectrum is a little bit different from before because here we lock Zupano to Sonata instead of Sonata to Zupano. This is kind of this noise spec is coming from Zupano. And so in summary, we have a good 1 micron ytterbium fiber laser with very clean spectrum and pulses, and the free running drift of repetition rate is below 0.3 ppm, and the relative timing jitter is also below 0.03% with very low timing jitter. So far, the laser working at 40 megahertz repetition rate, but we are happy to tailor the laser output parameters to your need. And so this is the end for my presentation, and thank you for your attention.